Good morning, everyone, or good afternoon. Depends on what time are you watching this video. My name is Ismail Gargouri, and today I will be presenting my research paper presentation titled A Multi-Layer Testing Framework for Automated Data Quality Assurance and Cloud-Native ELT Pipelines. So this work explores how we can combine orchestration level validation, DBT's declarative testing, large language models driven semantic tests, and cross-store consistency checks to significantly improve the reliability of modern ELT workflows. So I'll walk you through the motivation, the challenges, the methodology, and the experimental results, and we'll conclude with limitations and future work. So organizations today rely heavily on data to drive analytics, reporting, and machine learning models. However, ELT pipelines, they have become increasingly complex. How? We can say that distributed compute engines, evolving schemas, heterogeneous storage systems, and manual data transformations, they all introduce opportunities for silent data quality failures. Unlike traditional software, where testing focuses on code, data pipelines require continuous validation of data states. So a single undetected defect can propagate downstream and corrupt entire analytical systems. The core problem is that current validation solutions are not often fragmented. Rule-based systems like DBT tests or DEQ focus on structural correctness, but lack semantic reasoning. Machine learning-based anomaly detectors, they rarely integrate with transformation logic. Most importantly is that none of the existing tools validate across compute engines. This is problematic because DuckDB, Snowflake, Spark, and BigQuery, they all software related to data engineering, they may compute results differently. And finally, despite the growing capabilities of large language models, we have almost no research on using LLMs to automatically generate DBT tests. So moving to the challenges, technical challenges that must be addressed. First is detecting structural issues such as missing values or invalid types. Second is capturing semantic inconsistencies like invalid relationships or out-of-range domain values. The third challenge is by ensuring consistency between different execution engines. For example, DuckDB or Snowflake. The fourth one is by reducing manual test engineering using large language model generated constraints. And finally, maintaining acceptable runtime overhead so pipelines remain operationally feasible. These challenges, they define the scope of this research. The literature falls into four categories. The first one is foundational work defining data quality dimensions. The second is rule-based or statistical validation frameworks like Great Expectations and DEQ. Cloud-native validation systems such as DFDV that operate significantly on machine learning pipelines is a third category. And the fourth one, it is early AI-assisted validation methods, which focus mainly on anomaly detection, not declarative tests synthesis. So from the taxonomy in my survey, It is clear that no existing approach provides a unified multi-layer validation framework, and none evaluate large language model-driven test generation within DBT. So this leads to three gaps. No framework spans multiple validation layers of a pipeline, no semantic validation driven by large language models, and no cross-store consistency checks to reconcile backend differences. So these gaps motivate the design of a framework I propose. But before moving to the framework, my research is organized around four questions. The first question is, to what extent can a multi-layer framework improve anomaly detection? The second is, can large language model generated DBT tests add meaningful value? The third question is, how reliably can cross-store validation detect inconsistencies? And the last and fourth research question is, what is the runtime overhead of adding these layers? Everything in the methodology and results sections is aligned with answering these questions. This work makes four contributions: a unified multi-layered testing framework integrating orchestration, level checks, DBT validation, large language model generated tests, and cross-store consistency. The first empirical study evaluating large language model generated DBT tests in a real orchestrated ELT pipeline. Also, the third contribution is a reproducible implementation using Airflow, DuckDB, Snowflake, and GPT version 4.1 mini. The last contribution is a comparative analysis that shows improvement in detection, semantic coverage, and operational trade-offs. Here's the system design architecture. Data flows through Airflow, which orchestrates extraction, transformation with DBT, and validation layers. Semantic tests are generated automatically using a large language model, while cross-store checks compare the outputs of DuckDB and Snowflake. Each layer contributes differently. How? Because DBT handles structured constraints. Large language models tests, they detect semantic and relational inconsistencies, and cross-store checks identify backend level discrepancies. I hope that the structure is clear and visible. So moving to the Airflow DAG overview that contains the main tasks divided by layers. So the tasks included are extracting raw data into DuckDB, generating large language model-based DBT tests, running DBT transformation, loading results to Snowflake, validating cross-store consistency, and finally, logging and reporting results. The DAG ensures reproducibility and modifiability. Still in the proposed framework, we're going to talk about the large language model test generation workflow. This is a figure that shows a multi-layered data quality testing architecture. The workflow is divided in 5 steps. Step 1 is extract schema metadata from DuckDB. The second one is by constructing a prompt describing expected behavior. The third is by requesting a YAML formatted test file from GPT 4.1 mini. The fourth step in this workflow is validate the YAML for DBT compatibility. And lastly, execute the tests in DBT. So this allows the system to generate relational and semantic tests automatically. After creating our architecture, we need to evaluate detection capabilities, anomalies that were injected deterministically. So we have missing values, then invalid categories, referential integrity violations, duplicate keys, and numeric outliers. A fixed random seed ensures reproducibility, and this will let us precisely measure how many anomalies each layer detects. As you can see, we start by having a raw clean table, and we got later deterministic injection until we create anomaly table. Moving to the experimental results section, the summary of results is mainly we got 23.4% increase in anomaly detection from multi-layer validation. We got 74.2% of large language model tests that were useful, capturing semantic issues. We got also cross-store validation that identified discrepancies that DBT alone missed. Also, runtime remained under 1 minute. And the last main result is that 28 out of 30 DAG or DAG runs completed successfully. These results directly answer research question 1 and research question 4. So also, as you can see, this table is included in my paper. Moving to large language model test quality. Extracted from table 5 in my paper, we got 36 tests generated. We got 32 valid YAML, 31 executable, 23 useful. So these are the attributes that belong to the database that I used, which is an API from a football or soccer matches API. For the cross-store validation, it detected subtle differences between DuckDB and Snowflake, especially in the dim teams table. These backend level inconsistencies were invisible to DBT tests. The result strongly supports research question 3. Here, manual DBT tests detected 36 anomalies, while large language models tests detected 42. Combined, they detected 63 of 65 injected anomalies, which is a strong argument for synergy between human-defined and large language model-generated constraints. Full pipeline runtime was 58.6 seconds. The large language model generation step adds overhead but remains acceptable for batch pipelines. This suggests that semantic validation can be added without jeopardizing through output. So as you can see, the pipeline stage runtime is distributed. Extract data, we got 12.4 seconds. Generate large language model DBT test took 8.7 seconds. The run DBT models plus manual tests took 15.3 seconds. The run large language model generated test took 6.2 seconds. The migrate DuckDB tables to Snowflake took 10.9 seconds. And the quickest pipeline stage was the validation of DuckDB versus Snowflake, which took only 5.1 seconds. Total is almost a minute. So these results show that multi-layer validation meaningfully improves detection and mitigates blind spots. Also, large language model tests catch errors that humans do not write rules for. And by that being said, the large language model tests extend semantic coverage. The third main result, the main interpretation of the results, is that cross-store validation provides a layer of correctness beyond DBT, which means that it provides integrity beyond DBT. Also, the system is practical from a performance standpoint. It's because runtime trade-offs are acceptable for batch pipelines. Together, these findings show that our framework is both effective and feasible. But also, this study has several limitations. The main ones are the following. First, only one large language model was tested. Second, data set size was modest. Third, prompt engineering affects output quality. And fourth, results may vary for very large production pipelines. So based on the study that I've made, based on the architecture I proposed, the implementation I did, I could only do test one large language model. The results could be very different if I used more than one. The data set size really matters. Depends on the data you can use. The prompt itself, the prompt engineering, it's also a crucial factor because from an engineer to another, the prompt can be different, and AI models, they interact differently because they're case sensitive, because each word has its own weight in the agent and all that kind of stuff. And also because the very large production pipelines results can be different. So these limitations, they suggest opportunities for our future research. To conclude, this work demonstrates the value of multi-layered data quality testing in cloud-native ELT pipelines. Large language model generated tests extend semantic coverage. Cross-store validation ensures backend consistency, and the overall approach significantly improves detection while maintaining practical runtime overheads. This is one of the first empirical investigations to integrate large language model generated DBT tests into a real ELT workflow. For future research, I found that we need to explore tuned or domain-specific large language models. Also, we should automate repair of invalid large language model tests. I found also that we can apply this framework to enterprise scale data sets. And lastly, we can develop adaptive validation strategies that respond to data drift, because these directions would make automated data quality testing even more robust and autonomous. So that was all from me. Thank you so much for reaching this point and attending my presentation. I hope that this project presentation was clear and beneficial for you guys. Thank you so much for your attention. Thank you for Dr. Reza for providing this opportunity for us as his students to be able to work on a real world problem and make a survey paper out of it, and then a research paper that could be publishable. I hope that Each and every one of us learned something, and really looking forward to having your questions once you finish like watching this video, and I'll try my best to answer all your questions. Thank you so much again, and see you next time.